Hi all. In the previous lecture, we studied a system called Deuteron, which happens to be the most simplest of all the nuclei available for study. From the study of a Deuteron, we get lot of information, and one such information about nuclear forces is that it is highly spin dependent. As per observations, the spin of a deuteron is always 1 and parity is always positive. In the deuteron problem, if we are assuming a central potential and solving Schrodinger equation, assumption of a central potential places a restriction on the value of L, that L can take only value 0 because central potential has only R dependence and YLM theta phi is a constant, so there is no L dependence and L can take only the value 0. And therefore S can take only the value 1 because I is a resultant of L and S. I is already 1. So when L is 0, there is only one possibility for S, that it can take the value 1. Okay. Now, if the assumed potential is non-central, if we assume that the potential is non-central, then it means that other values of L can also be considered other than L equal to 0. They will also contribute. But we know the parity is computed as minus 1 raised to L. And we know from observations that parity is positive. So we have to rule out all odd values of L. Only even values of L can be considered as per this relation if parity is to be positive in the case of a deuteron. Now we also have a restriction for the L different values that L can take because I can take only the value 1. So the possible values of L and S, if we are assuming a general non-central potential, is L equal to 0, S equal to 1 and I equal to 1 is one possibility. The other possibility is L equal to 2, S equal to 1. Then the resultant I can take values from L plus S to L minus S, which would give me 3, 2 and 1. So in both these cases, I have the possibility I equal to 1 appearing. Okay. So for the most general case of a non-central potential, the ground state of a deuteron is not actually purely L equal to 0 state. It is actually a mixture of L equal to 0 and L equal to 2 states. It is like more of L equal to 0 and a little bit of L equal to 2. Okay. So we see that from all these considerations, we see that there is a there is a restriction or there is a preference for a particular spin value, even though different values are possible to be taken. When I say that, what do I mean? See, my neutron and proton are spin half particles. So my Sp and Sn can take values half. And if I look at the resultant spins, it can be like this. Okay, it can be. So three possibilities. If I club for all these are the projection values that I have written. SZ values I have written here. If I combine these or if I take all these three projection values as a single group, I can say that these values arise from S equal to 1. S equal to 1 can have projections plus 1, 0 and minus 1 all quantized in units of H cross. Okay, and this value SZ equal to 0 can come from S equal to 0. So when I have two spin half particles, I have an option that S can be 1 and S can be 0. But in the case of a deuteron, I see that I am never getting this possibility. I am getting only this thing, capital S equal to 1. So this indicates that certain spin values are more preferred, or there is a preference for a particular spin value over the other, even though theoretically both these values are possible. So that is why we are telling there is a spin dependence for nuclear forces. Now, if this is so, we have seen that there is a spin dependence. So the Hamiltonian also should contain a spin dependent part. And this spin dependence is introduced in the potential term, and we add a spin dependent component to the potential term. The term added is similar to the ones which are used in atomic spectroscopy, where we discuss about LS coupling and splitting of states as say 2p half, 2p 3 by 2, etc. We explain it by the addition of a term L dot S. Okay, so we explain that by spin orbit coupling, and we have a term L dot S coming in, and that is how we discuss the splitting of states due to spin orbit interaction. Here also the spin dependent component is very similar to the terms used in atomic spectroscopy, and the spin dependent part of the potential is represented like this: Vs of R Sp dot Sn. Now when we introduce such a term in the potential, then the Hamiltonian becomes different for S equal to 0 and S equal to 1. We will see how it becomes different. Okay, we know capital S is the resultant of Sp and Sn. Now if we are squaring and obtaining the magnitude, S square would be Sp square plus Sn square plus 2 Sp dot Sn. So from this you can obtain a relation for Sp dot Sn as S square minus Sp square minus Sn square by 2. Now consider the case when S equal to 0. When S equal to 0, Sp dot Sn will be, now what is the magnitude of all these angular momenta? It is actually, when S is 0, it will be 0 into 0 plus 1 h cross square. When this is the case, both these are spin half particles. Sp and Sn can take values half. Then the magnitude of angular momenta would be like this, and we get Sp dot Sn as minus 3 by 4 h cross square. Similarly, when S equal to 1, you just plug in, instead of 0 here, you just put, when S equal to 1, it will be 1 into 1 plus 1 h cross square. Then minus, these terms are the same. But you evaluate Sp dot Sn, you see that it is plus h cross square by 4. So the potential term appearing in the Hamiltonian will of course contain Vc of R plus a spin dependent term, and the sign of this term will actually depend on the value of Sp dot Sn. We see that Sp dot Sn is negative for S equal to 0 case, and it is positive when S equal to 1. Okay, so when this term becomes negative, the depth of the potential well actually changes. When this is negative, the depth of the potential well reduces, and when this term is positive, the depth of the well actually increases. We also know that the binding energy of deuteron is very small. It's very small. It's a very weakly bound system. The binding energy per nucleon was something like 2.225 MeV. The binding energy is something like this. So binding energy per nucleon would be 1 point, you divide it by 2, it would be 1.1 something. That value is very small compared to the value that most nuclei have. Most nuclei have an average binding energy per nucleon value of approximately 8 MeV. Majority of nuclei fall in that range. So when we consider that the binding energy of deuteron is very small, and now we saw that the well depth is different when s equal to 1 and s equal to 0. So it is that when the case is s equal to 0, the depth of the well is not sufficient enough to bind the proton and neutron together as a single system. Whereas when s equal to 1 is the case, then the depth of the well is sufficient enough to hold the deuteron as a single system, as a bound system. Okay, since the binding energy is small, when the well depth is small, the proton and neutron escape from the well. They are not bound together and they are moving like free particles. So, for the case when S equal to 0, or you call that potential singlet potential, when the potential is singlet potential, the well is not attractive enough to hold the proton and neutron together as a bound system. Whereas when the potential is S equal to 1 or triplet potential, the formation of deuteron is favored because the depth of the well is sufficient enough to hold the proton and neutron together as a single system. So S equal to 1 potential or triplet potential is more attractive compared to S equal to 0 or singlet potential. Okay, so this is one observation which suggests that nuclear forces are highly spin dependent, because even when theory suggests that various spin values are possible, it is observed that only certain spin values are taken by nuclei. I hope this content was clear. Thank you.